Hello, welcome back. In this segment, I would like to introduce a way to solve an optimization problem, for example, like a traveling salesman problem, which I will define in a moment, using model checking. Let's take the simple example of a traveling salesman problem. Let's say you have a bunch of cities and you need to visit all of them and come back to the place where you started, maybe your hometown you start, and then you need to visit all the cities. There is a goal, of course. You want to minimize the distance you traveled because maybe more distance means more expensive. So how can you organize such a tour of visiting all the cities and come back to the place where you originally started? Of course, you don't want to visit the same city multiple times, so you need to make sure you visit only once. Okay, how do we approach this? There are many algorithms. If you search online, you will see random algorithms randomized algorithms, I mean, simulated annealing, hill climbing, and something based on the Dijkstra's algorithm. It's extension of that A star. There are variants of that. What I'm going to show today is a slightly different approach. It's kind of a higher level of abstraction where you just declare the problem and you let the reasoning engine to search the state space, if you will, of different possible tours and come up with, something close to optimal. So that's the idea. Okay, so traveling salesman problem can be visualized as a graph, right? You have a bunch of cities. Let's say here's one city, another city. Just make it simple, four cities, right? And I'm just connecting them. It's a complete graph, meaning every city is connected with everything else, right? So like this. And there is a cost associated with it, maybe a distance, kilometers or miles or whatever. Um, all of them have distance, and it's usually symmetric matrix. If you visualize this as a matrix, it's a symmetric matrix because distance is usually commutative. Okay, so with that background, right, the question now is how can I start at one city? Let's say the city names are 0, 1, 2, 3, like easy to store in a computer. And we will, let's say, start at city 0 and visit all the cities and come back to the city that you have started. Okay, and you don't want to visit the same city again and again. And you want to find a good tour which minimizes the cost. There is a cost associated within every city, right? Let's say 10 here, 20 here, 5 here, and 7 here, whatever. And then let's say 6 between 1 and 3, and 9 between 0 and 2. So you want to start at the city 0, visit all the cities, and come back to city 0 in such a way that if you count the total cost, it should be close to optimal, minimal, whatever. Yeah. Okay. Ideally optimal. So how do we programmatically do this? Of course, there is a brute force you could do, right? You fix a particular city, 0, try to explore all of the things. You can go from 0. You can try that kind of brute forcing. It's usually very, very expensive. If there are n cities, you are going to do order of n factorial because there are that many um, tours possible if you were to enumerate all of them. So for large n, even if n is 10, you're already talking about billions of possible tours. If there are n cities, you may get billions of tours if n is 10. Okay, so that's not what we want to do. We want to do a little bit better than that. And at the same time, we don't want to program the algorithm in this approach that I'm going to talk about. I'm going to use the spin Promela model checking idea to approach this problem. Okay, so I'll show you how distances are stored. Let's say I have only 5 cities and I will store them in a one-dimensional matrix because the language that I'm going to use doesn't have two-dimensional array. So we can definitely store a two-dimensional array in a one-dimensional array, right? As long as we know the number of columns, which means the number of cities, we can easily traverse it and extract the individual distance between any two pairs of cities. Okay, so how to interpret this, for example, let's say you are at city 0, the distance to city 0 is naturally 0. to 1 is 68, to 2 is 12, and so forth. So we have this distance matrix encoded here, and nothing else is here, right? It's just a bunch of initializations. Where is the model then? The model I'm going to talk about is here. It's a spin model checking in. It's called Promela high level abstraction language to characterize the problem. First, we need to initialize the distance, and that's exactly what I just showed you a minute ago. And we have state variables. We have the position which runs from 0 through n. There are n cities, and cost is the total cost of the tour, and we have a Boolean variable to mark if all the cities are visited. So what we do is at the beginning, the cost is 0. We start at position 0. The tour is not complete, and all of them are not visited. So we set it to false. What we do, this comment is not quite right. I have fixed the starting city. The starting city is 0. City number 0 is where I start. And then I let spin model checking to randomly pick the next city to visit, right? You see here, select next means randomly pick one, non-deterministically pick one between 0 through n minus 1 when the position is less than n, meaning we have not visited yet all of the cities. So it will pick in such a way that we have some constraints here, right? Can we visit this city? So let's say it picked one city, and the next is one city. And if it is not visited, we mark that next city in our tour. And we just say we visited the city, and then we increase the cost. And here is just the basic math to convert one-dimensional array to two-dimensional array, because we are talking about distance between pairs of cities, between tour of position minus 1 and the current one, right? And then we increase the position. So this is not algorithm per se, right? This is just declaring how the model checking should traverse our state space. And if position is n, that means we visited all the cities. We have to go back to the initial city. That's the reason why we take tour of 0, and we mark the tour to be complete. Okay, so this is just characterization of the state space, and then we are just printing the result here. Okay, I'll come back to the never climb in a moment, but this is the basic idea of traveling salesman problem, using some kind of domain-specific language, if you will. Okay, so we can use now the spin model checker, right, to just generate some random tours for us. Let's say, don't worry about the warning never climb. I will come back to that in a moment. For now, you can just see if I run it again, I get a different tour. Okay, so you have a tour which is 202 cost. Here's another tour which is 257. If you add the distance between the pairs of edges connecting these nodes, right, 0, 3 plus 3, 1 plus 1, 4, and so forth, you will get 257. Similarly, 220, if you take this route, there may be better routes, we don't know. Here is somewhat expensive, even more expensive. And here is 200, better. So I'm not going to keep on running it, but I just want to show you the simulation, random simulation is already giving us some solution. But let's say 200 is a solution for a moment. We are going to ask, can we get better than 200, right? Better meaning less than 200. We can try that idea. So what we're going to do, let me first show you even within the traveling salesman model, where are we encoding that? So here is the way I'm encoding. So if the tour is complete and the cost is less than or equal to bound, we break, meaning we found a tour which is bounded by whatever number we pass in. Let's say if the tour length is 199, and if we send the bound to be 200, this never condition will be violated, which means we found a better tour than what we have currently. So we can keep running this by changing the bound, for example, using binary search or whatever. We can find optimal very quickly or close to optimal. So let's try this idea for 5 cities, right? Which is what we have. And we will make a bound of, say, less than 200, right? We want, say, 199. So how do we do that? I need to recompile the spin with the bound, right? Say, I'm going to put 199. Let's see whether there exists any tour below 199. It's not going to show the output right away. I need to recompile this with some special flags. I'll give you, I can just do it for this small demo. No special flags is needed. It generates a file called pan.c. If you know my previous demo, I talked about spin generating a pan.c file. And then I can just run pan. You see here, there are no errors. That means my tour, there's no tour below 199 or equal to 199. Let's confirm that, right? Let's check whether there's a tour for 200, which we found through random simulation anyways. Let's compile and run it. Yeah, we have one error, which means the never block is violated. That's what it says. Uh, it is basically the never climb violated. You see here, never climbs generated has some problem. So we will look at the trial. It generates, there's a trial file -t. Yeah, you can see the cost is 200, and here is a tour. It starts at 0, 1, 4, 3, 2, 0. This is the best tour. You cannot find a tour better than 200. Okay, let's do something different. Let's say we say, is there a tour below length 225? And we will recompile and we will analyze. Hopefully there is one. You see here errors one. That means a new trial file is generated. So a trial file is a dot. There is an extra something here, dot trial, which is automatically analyzed when you do with the -t. And it found a tour cost 204. Remember, it's not going to find optimal right away because the goal of that never block is to find a tour less than the bound. Okay, now let's increase the bound, right? To 200, decrease the bound to 202 and try this and try this. Yeah, it has an error. So let's see whether we get a better tour. Yeah, we found a tour of cost 200, which is better. And how do we stop? Like, let's see. I put 199, and if there is no tour, there's no errors. That means none of the never block. The condition that we put inside the never block was never violated. So there are no errors. Okay. But I just played with 5 cities. Not a big deal. The real challenge would be, let's say, 15 cities, and then slowly increasing the number of cities. Let's go back to my traveling salesman model, and I have another matrix of distance for 15 cities. And now we will see what happens. Okay, let's just run it without any flag and see whether we get a random tour. Yeah, 845, 692, 661. So we get different costs when you run it again and again because it's random simulation. Okay, so we are able to find something like 661 seems to be an interesting number, but we don't know whether there is anything below 661. Let's try using our model checking here. Anything below 661, that means 660 or equal to, and we will analyze it with the model checker. Pan.c is what it is generated, and it's going to take a little bit time because this is long one. Yeah, it found an error. One error, which means, yeah, we found a tour which costs 771. What did I do for this? No, there was my random simulation. Sorry. I was surprised because we already have much better than that. I need to remove that -a flag. Now it should be -t. And that should tell us, yeah, it found a 656 cost. Remember, random simulation gave us something like 661. Now we found 656. Let's try whether we have anything below or equal to 665 and recompile. Okay. It's going to take a little bit time, but yeah, you have an error. And now let's try whether anything. Yeah, we got 647. So we can keep trying with small costs and see how close we can go. This is not a complex thing to do because it's binary search essentially. You could just start with a large number. Every time you get a better tour, you can just divide it by two and then continue. So you can try that in logarithmic steps. You will be able to find a better tour if it exists. So the point is here is 15 cities only. It's still you saw some problems. It's already getting slow. Let me show you 25 cities. Okay, this is going to be interesting. Hopefully interesting. Let's see. I'm going to try with 25 cities. It's going to take a fair amount of time. All right. First, let's see whether we can run it without any flags and see some random simulation, right? Yeah. Never climb is used in random simulation. It's just going to try to traverse the graph, see whether it can produce anything. Yeah, it found a tour which cost 1,447. Let's try again. It's just trying to find a path that visits all the cities that are not visited and come back to the original starting location. See, it takes time now. The previous one was quick and this one is taking time. As you can see, it's getting challenging now. So what I'm going to do is I will go ahead and generate the pan model we did with the -a flag. But I'm going to use the -1447 as the 446 and let's see what happens. Now pan is generated, but this time I'm going to use some extra flags because otherwise it's not going to scale. Let me show you why I say so. It's going to, okay, it found a tour, which is pretty good. It was pretty quick. And let's see whether, yeah, 1,279. Pretty good. We're trying with 25 cities. A lot of possible tours we can do, but it found it very quickly so far. And now let's try again with something below. 1,278. Just curious whether anything below. But you don't usually decrease it by one, right? You would just try something half of this, for example. Let's say 800. Now it may struggle because maybe there isn't any tour of length below 800. So it's going to try a lot of possible tours. And under the hood, it's going to build a state machine of so many possible states. And it may struggle now. You will see soon. No, no, don't worry about the depth states and things like that. This is internal information about the state machine. Oh, you see, it's killed now. It's not able to scale when I put bound to be 800, meaning find any tour below 800. But if I are to put, say, 1,000, we already found a tour of cost 1,279, right? Let's try 1,000. It may struggle again. It is struggling. We are saying there are 25 cities. Find a tour. The cost of the tour should be less than 1,000, or less than or equal to 1,000 rather, in this case. Okay, it's killed again. So it's not good. It's not able to find anything like this. So luckily, we can do some small tricks. There is some kind of advanced state 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 compression mechanism in Spin. It's called bit hashing, and I will use the bit hashing to do. I'll use the bit. Yeah, do not worry about the bit state and no reduce for now. So it's a way to create a hash table without storing all the state information. Some partial information will be stored. Okay. We are trying with 1,000, by the way. This is the same bound. And then I'm going to use a pan with a minus W. I think it was -W. Yeah, let's try this as it is for now. See whether it's finding anything. I'm trying with 25 cities for 1,000 as the maximum. The random simulation already found tours of cost 1,200. So we're trying to keep reducing further, right? So far, no luck. So this is not representing all the states with full information. It's only partial information. That's right. That's the reason why it's taking more time. But in any case, you can see increasing the number of cities and putting tight bounds will make the state space large to search for an optimal solution. So far, no luck. So I'm going to use another flag. Don't worry about what this is to make it slightly faster. It may find a tour. Maybe there isn't any tour after all, less than or equal to the 1000. It's exploring for a long time. So I'll increase the bound to show you the value of bit state representation, which is pretty fast. The cases that I tried. What I'm going to do is I put a slightly larger bound, let's say 1100. And then I'll try with bit state representation. Okay, so in this case, we did not find a tour because there are no errors reported. As far as I can tell, there are no errors. Oh, there's an error here. I have overlooked it. So let's see whether we can look at the tour. Yeah, there's a cost of 1099, which we couldn't find without the bit hashing. We can try that. I'll just have this and recompile without the bit state and no reduce. See whether it detects a tour of length 1099. It may get killed. Who knows? The problem with the bit hashing technique is that it's not storing the entire state space. Therefore, when it terminates without any errors, it doesn't mean there are no cheaper tours. But if it does terminate with some errors, usually there is a tour it produces. Okay, you see it's getting killed now without that bit hashing technique. What I have shown to you today is domain-specific language, formal methods community they use for representing state space at high level of abstraction. And then I let the search engine behind these kind of model checkers to search the state space, generate the state space, search for interesting paths to satisfy the invariant that I put in that doesn't exist any tour, but it was trying to contradict that if it contradicts, it finds a tour for us. Okay, that's all. Thank you very much for your attention.